firm dynamic. Um, we were discussing this model of firm dynamics where firms are deciding to enter or exit depending upon their productivity and 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 maximizing their expected lifetime stream of profits. Okay, and we finished the equilibrium, the definition of the equilibrium, and I will just reiterate myself. So there are two important things in this model. The one is the zero profit condition, which is going to be present in any firm dynamics, most of the firm dynamics model, including Mallett's, Oppenheim, or whatever you guys are interested in. A zero profit condition is nothing but uh, the condition that tells you that what is the threshold, what is the minimum level of productivity that we require to operate in this economy. Okay, so that pins down basically the Z star. The second most important condition is the free entry condition. The free entry condition tells you that what will be the price in the economy. Okay, so if the price P of the good is very high, then the value of entry is very high. That means a lot of firms will enter. If the price P is very low, then that means the value of entry is very low. Nobody will enter. And in equilibrium, it should be, we will always look for an equilibrium where M is positive, M is the mass of entrants. It should be the case that it equalizes. Okay, ex ante, there is no excess rents in the economy. So let's say these are quasi rents. Okay, there are no absolute rents, but there are quasi rents in a sense that ex ante, there are no profits that can be made from entering this economy. Expose, some firms are going to make profit, some firms are going to make losses. So there are these quasi rents that one can make, but there are no absolute rents that can be made in this economy. Okay. Uh, then we also said that there will be a goods market clearing, which means that given this price that is pinned down by the free entry condition, you have to make sure that the total demand for the good at that price equalizes to the total output of the economy. Okay, so this is different from what the models you may have studied before, where prices are pinned down by the market clearing. Here, it's not the case. The price is pinned down by the free entry condition, and market clearing pins down the number of firms that will operate in the economy. Okay, so given the price, if there is a lot more demand, there will be a lot more firms that will operate. If there is a lot less demand, then there will be small number of firms that will operate. That's what you need to know. Once you know this numerically, it will be very easy for us to solve this model. Are there any questions on this? Okay, so let me then tell you few logistics of the stationary equilibria. Okay, so remember, in stationary equilibria, we need to know the value of the firm, which is the discounted sum of future profits. We will always know the output because that is the amount that I want to produce, conditional on my productivity. I will know the cutoff productivity from the zero profit condition, and there will be a stationary distribution of firms, which means that number of firms will not change in the economy. There will be entry and exit, but that will be such that distribution of firms will not change in this economy. Okay, so the entrants will replace the exiters. Okay, so how do we pin down this distribution? That's the one of the most important object of this model. To pin down this distribution at any period t plus 1, that is denoted here by z dash, at any period t plus 1, the distribution is going to be an object which is a combination of distribution of firms in time period t times the probability of survival. Okay, so there is a distribution of firms for each productivity type. Some firms will exit, some firms will survive. Okay, and this fee matrix is gonna contain this information on the survival of the firms. Okay, plus there is an entry of firms. So M was a mass of entrants, and these people were like taking out the balls from the bags. Okay, so each distribution type will be entering into the economy every time period. So the new distribution will be the changed, the survival adjusted distribution of the existing firms plus the mass of new firms at each point in the productivity. Okay. So what is this fee matrix? It's a combination of the transition. So remember we said that productivity fluctuates over time. This is the idiosyncratic risk. Sometimes firms are very productive, sometimes firms are very unproductive, and we said that productivity will follow a Markov process. Okay, so what is the Markov process? Was that, oh, conditional on your type, we know what's the probability that you will jump from Z1 to Z1 or Z2 to Z from Z1 to Z2 or from Z1 to Z3. Okay, so we know all these probabilities. So from one period to another, you can jump from these different states of the world, and we know the probabilities. So we can actually assign how much will go, how many firms will jump from each one state to the another. Okay, that's f of z bar z dash given z. That's the transition probabilities that are given. But all these people who are jumping from Z1 to Z2, Z1 to Z3, Z1 to Z4, some of them will not survive the market, right? So all the people, let's say Z threshold, Z star, below which nobody produce, let's say it's Z2. So all the firms that will transit from Z2 to Z1 or Z2 to Z2 or Z2 to anything below Z3, they will exit. Okay, so there you have a mass of firms will be 0. So this is what it is capturing. So you want to only put the positive mass of firms when Z is greater than Z star. Okay, otherwise these firms are gonna exit the market. So this a combination of these two things will give you this conditional distribution. Okay, this is kind of a conditional distribution. So I know how many people will jump from Z1 to Z1, Z2 to Z1 to Z2, Z1 to Z3. Then I will say, okay, people who are jumping from Z1 to Z1, they will not survive out. Z1 to Z2, they will not survive out. Z1 to Z3, yes, Z3 is okay, you can stay. Z4 is okay, Z5 is okay. So this will I will keep, and I will add the entrants to them, and then that will be my mu z t plus 1, which is mu z dash. Okay, so in equilibrium, the distribution mu will be stationary. We said that the distribution will not change. Therefore, t plus 1 distribution should equals to distribution at z at t. Okay, so that's why you can remove this subscript dash, and you can write in matrix form that mu should equals to phi times mu plus m times g, where g is the exogenous distribution of the entrants. Okay, mu here is a n cross n. Mu is a n cross 1 matrix, which is telling you for each productivity type. So let's say there are n productivity types. What is the mass of each productivity type in the economy? P is this transition matrix conditional on survival. This is n cross n matrix. Mu is again n cross 1 matrix. G is again n cross 1 matrix because it's telling you when you are drawing the balls from the bag, what's your probability to draw Z1, Z2, Z3 until Zn. Okay. So this from here you can get mu very easily. So mu here you see, like I know my phi, I know m, and I know g, so I can get mu out of this equation easily. Okay, so we'll get back to this in one slide. So how do we compute the equilibrium? How do we solve this model in the computer? So we will guess an output price P naught, any price. It's kind of a starting price because we don't know. We will guess something, and I will tell you what the guess can be. It's kind of an guess is an art. and you need to be careful with this. Given the price, I can compute firms' policy functions, the Y, the output, the labor demand, and the profits. Okay. So I can compute today's profits. Okay. I, I can then compute for each productivity type what who will continue to produce and who will not produce. Okay. So therefore, I can get you your lifetime value of production, lifetime discounted sum of profits. So I can get the V for each productivity type given this price at this price. Okay. Then I can use this continuation value to pin down my Z star, because this is so maximum of 0, and this continuation value will tell me who will survive and who will not survive. So this is zero profit condition. Okay. Once I have the zero profit condition, then I can see if this P naught satisfy the free entry condition or not. So I know the V, then I can compute what is the expected value of entry. If the expected value of entry is exactly kappa E, then P naught is the true price in the true equilibrium price. Okay. If this LHS is too high, it means price is too high, value of entry is too high. So you need to adjust your guess, let's say P1, which is smaller than P naught. So you need to adjust below. Okay, and then you need to redo all these steps. So you again solve for value, you get your E star, you again solve for your free entry condition. Now, if your left hand side is lower than kappa E, it means prices are too low. So then you need to increase your price. So you need to keep on doing it until your free entry condition satisfies. Okay, and this is we will do it in the in numerically in MATLAB. Once you have pinned down the price, rest is very easy. You know this the law of motion of firms, the distribution of firms is given by this equation, which you can invert. So if you take phi times mu on the left hand side, and then you can bring back the inverse of the I minus phi on the right hand side. So your mu is nothing but m times I minus phi inverse times g. So you know phi because you know that Z threshold from here. You know G is exogenous. You don't know M, okay? So you don't know M, but to any M is a scalar. So M will rescale this distribution up or down. Still you don't know M, okay? But to the scaling factor M, you know what's your distribution of firms will look like. But you don't know exactly what M is. The M will be pinned down by exactly the goods market clearing condition. Okay, so M is actually the number of, here it's the mass of entrants, and I will tell you how to pin down the M using the goods market clearing condition. So here how we will solve actually the model. So for any firm I, like you can write down the price profits like this, and the expected value of the continuation value is nothing but the probability of I jumping to J and the value function at that J. Okay, so again Z, so the productivity Z is a Markov process. There are n different states that you can take. So if I want to compute the expected value of continuation, then I need to take the probability times the value for each state of the world. That's what I am doing. So this is the expected value of continuation. So the value times the probability itself. Okay. So this is exactly how will you write the code in the MATLAB in any programming language basically. Fij is a transition probability that you know, and YJP you do not know, right? So again, you have to here make a guess on the YJP in order to compute your this value of the firm. Okay, so we will use this logic of dynamic programming where we will use the value function iterations to get our value of the firm, and I will show you how to do it. Okay. So how to do it is you will guess any starting value for each productivity type. Now this value should equals to the profit today plus a continuation value. Okay. And then sum should be that value itself. Now, if it is this is different from your initial guess, then you need to redo this process, and you will do it until your guess converges to the true value of the firm. So there are two loops. There is a loop on the prices itself, and there is a loop on the value of the firm given the prices itself. So there is a loop inside the loop. We will see it uh, uh, in half an hour or something. But remember, for given price, we need to get the value of the firm. This is not trivial. Okay, we know the profits, but we do not know the value of the firm. So you have to guess it, and from that guess, you need to re-update your guess until you have converged to the true value of the firm. Is this clear? Okay. Once you have the value of the firm, then you can just write the value of entry, which is again, what is the value of entry? It's the value of being a type I times the probability of being type I, and you will sum it up. This is the expected value. So if your probability of becoming a type I is 0.2, then you will say this times 0.2. If probability of becoming a type 2 is 0.3, then this times 0.3, and then you will sum it up, and this should equals to kappa E. Okay, this should hold in equilibrium. Okay, so the exit decision is simple. Exit decision is that given P star, the incumbents know their value function VI P star. The exit threshold you can find then where given P star, you need to find the minimum I, the level of productivity, such that the continuation value is greater than 0. Okay, we know that the continuation value will be increasing in the productivity of the firm. So you need to find the minimum V, the minimum level of productivity above which everybody has a positive continuation value. So that pins down the Z star numerically. So the continuation value is nothing but the probability that you will jump from I to J times the value of being J. That's your continuation value, right? So the minimum productivity level above which your continuation value is positive will pin down your Z star in this economy. Okay. You will collect this exit decision such that if Zi is less than Z star, then you will exit. And if Zi is greater than Z star, then you will not exit. So this X becomes my like a column vector of this exit decisions that I will collect all of them together. Then this column vector, I can use it in the phi to get my mu, which is the stationary distribution. Okay, so this P is for each productivity type I who is going to jump to J, given the P star is going to be the transition probability. This is given to us 1 minus the exit decision. Okay, so if the probability that I jump from I to J is, let's say, whatever it is, then if I am exiting at that level, then this is 1. So therefore, phi at that level is 0 because these firms will disappear from the economy. If I'm jumping to a level J, but this then my exit decision is 0, that I am not exiting, then this will be 1 minus 0, which will be 1. It means that you will remain in the market and your probability is FJI, okay, which is the mass of firms that are jumping from I to J. Is this clear? This is bit technical, but please let me know. This is exactly how we will put down the model in the computer. Okay. Now, how to pin down this M? This is where the goods market clearing condition will help us. Overall output in the economy is going to be the sum of output by each type I times the number of type Is in the economy, right? So this is the distribution which we computed with the scaling factor M. Now, what is M? You can compute from here. So we will use the fact that total Y should equals to total demand. This is the goods market clearing. Now we know that mu MP star is nothing but M times this matrix here. Okay. So I can take the M out because M is a scalar. So I can take the M out. And if I take the M out, then I can take the rest of the things below as a denominator of dP star. So M is nothing but the total demand divided by the total output computed when M is equals to 1. Okay, because M is a scalar. M I can just take it out, is a scalar. So I can compute M star from this. So it's basically saying that M is a scaling factor which will scale up or down depending upon the overall demand in the economy or how large is the economy, but it will not affect the prices and the distribution of firms. Okay, again, the prices P are pinned down by free entry condition. The mu is a combination, the stationary distribution of firms will be a combination of M and P star. So for instance, let's say there is a distribution of firms. There are two types. There is type Z1 and Z2, which is will be given by mu. Let's say mu Z1 is 100 and mu Z2 is 100. So there are 100 firms of each type. That's what mu is. Okay. What does it mean that I want to compute mu for M equals to 1? It means that I will just rescale it in a sense that instead of saying 100 firms each, I'm going to say there is a 50% of the firms are for Z1 type and 50% are the firms for Z2 type. So I will divide these two things by the total number of firms in the economy. Okay, so that's what we mean that M is a scaling factor. If M is higher, you just multiply the distribution by M. If M is lower, then the overall number of firms will be lower. Okay, but it will not affect the distribution of the firms. It will always be the case that 50% are Z1 type and 50% are Z2 type. It could be that overall firms are 50-50 or like 100-100, 200-200, 300-300 or 1-1. That we don't care about that. We care about the distribution of the firms. And once you have the distribution of the firms, you can get M, which is that, oh, we know it's 50%, 50%, but I want to know what the exact number of firms are. That's where you need the scaling factor. Is this clear? This is very important. Okay. So there is a probability of a corner solution. We will just ignore it because we don't want to look at it. So the model we will solve today is going to be calibrated or estimated to these parameters. Okay, I will tell you how to estimate it and how to calibrate it. Calibration and estimation are two different things. What we did yesterday was structural estimation. What are we going to usually people do in macro models is calibration, which means that all the parameters that you see here, they do not provide the standard errors on this. Because models are highly nonlinear, you cannot solve it for many different values of the parameters so that you can get the standard errors. So there is kind of a simulated method of moments that people do to get close to the moments you want to match in the data, but still most of the macro papers where you will not see the standard errors on the parameters. For instance, here I'm saying I want to calibrate beta equals to 0.80, but I'm not saying what's the range of beta is. Yeah. So the calibration here is gonna be, so I have a production function, I need alpha. Alpha I can estimate with the production function estimation techniques that we discussed in the first class. Here I'm going to assume it to be 0.2 by 3, 0.66, just like it's for presentation purposes. But when you do like use in your research, you need to be careful what alpha is. I will use beta, which is the discount factor of 0.80. I'm going to use the fixed cost of production as 20, the fixed cost of entry as 40, the serial correlation of the AR1 process to be zero point 0.9 here. This is a Z, like it's the average of the distribution. I can assume it to be 0, doesn't matter. Here I'm putting it to be 1.40. I will tell you why it is like why I am doing it. It's not a big thing. I'm going to assume that aggregate demand in the economy is fixed. It's 100. Remember, aggregate demand in the economy, this pins down M star. I'm assuming it doesn't vary with P star. It's kind of a like strong and unrealistic assumption. Of course, you can make it responsive to price in the economy and all those kind of all those kind of things. It's just for presentation purposes. I'm assuming the upper bar to be 100. Usually, you match the size of the economy by the population or the overall employment, the endowment in terms of labor in the economy. I will approximate this AR1 process in 101 or 100 different levels. So remember, this productivity is a distribution. It's a continuous object with it's an infinite dimensional object. But when you solve it in the computer numerically, you have to discretize the productivity distribution. What does that mean? You cannot solve for like each productivity that a firm can take, because there are infinitely different productivities within any distribution. Okay, so we will say we will divide this distribution into, let's say, n different parts or 100 different parts. So here I am doing it for 100 parts, and firm can only take one of these 100 different distributions. And I will assign the probability of taking each of these distributions. Okay, why how we can do this? We are not discussing that in this workshop. There is this whole literature on Gauss quadratures, which explains you how to do it. We will just use a code that is being used very frequently in the macro literature, and you should be very happy to use that as well. Nobody will question you why you are using this. Okay, so the discretization process we are not going to discuss, but I will give you the code and I will explain you how to use that. So let me actually, I just want to go very quickly to tell you what happens. So if yeah, so let me open here. Uh, no, where did it go? Okay, so let me open Paint. So if I just quickly show you how the discretization happen, it will be good. So imagine if this is the x-axis. Imagine this is the distribution of Z. This is the productivity distribution. And I'm dividing this distribution into 4 different levels. So this is so this is my Z1, Z2, Z3, Z4. Okay. I'm saying firms can be of one of these 4 types. There is a probability assigned to each of the types. So how I am going to do it? I'm going to say all this mass will be correspond to this type. All this mass will correspond to this type. All this mass correspond to this type. All this mass correspond to this type. Okay. If I have a sufficiently high number of Z's, you can imagine that measurement error will not be that huge. Okay. You are also imagining what happens on the left-hand side, this part where I'm actually leaving behind. I will leave it or I will assign it to Z1 as well. There are two things. Either I leave it and divide it by the overall mass of firms that I have so that the total sum is equals to 1 because sum of the distribution should be 1, or I can assign it to Z1 as well. Under what condition you can do it, what is the right way to cut the distribution, that's the literature, that's this Gauss quadrature literature that I was trying to tell you about. We are not going to discuss it, but remember, this is the kind of the algorithm that goes behind in discretizing any continuous distribution. Okay. Are there any questions?
Just to confirm in
Yeah.
this, you have you've assumed 100
Yeah.
probability
Yes.
productivity.
Yeah. Go ahead, Rishi. I could not hear you.
Yeah, I was just saying that, just confirming.
Yeah. Yeah. So we cut it into 100 different levels, actually 101. So that you see, like here, if you cut it into 4 parts, then you have 5 different regions. So we always cut it into odd number so that you have even number of regions. It's nothing. I will tell you why it is okay, why it is good to cut in odd number of regions, because then you will always have a 0 in between because it's a normal distribution. But yes, uh, it's not a innocuous assumption. The economy, the result, everything depends on how you cut this distribution. Okay, so I'm not saying it's doesn't matter. It matters a lot. But given what we want to understand, which means, okay, I wanna understand that how firm dynamics change when there is a higher cost of entry. Then you will always compare economies that are reasonably equivalent, such that you will not change the distribution of the grids. You will not change the parameter space. You will only change one thing, that is the cost of entry, so that the two economies are absolutely equivalent apart from this different cost of entry. Okay, so you cannot like just randomly have 100 node points for one and 200 for other, and you say, oh, I find these different results. That's not what should we do. We should keep everything the same and change only one parameter at a time, so that the inference you are drawing from the model is valid. Okay, so the
Sorry
value
to
function. Yeah.
cut you. Yeah, sorry I joined late. I just wanted to know, you said something about the odd number in the discretization process.
Yeah.
So
Yeah.
why that odd number is important?
It's not important. It's not important. It's just that I do it because you will all you will always get in the middle the 0. So there will be equal 50 negatives, 50 positives, and the 51st will be 0. And that's because I'm assuming a normal distribution, but it's not important at all.
Right,
You,
because you just define the grid space of that
yeah, yeah,
G,
yeah,
and then you said that the Markov chain process will follow on this
yeah,
G.
yeah,
So when you write the code, you just apply the Markov chain on that
yeah,
grid space.
yeah, exactly. Yes, it doesn't matter. You can choose. I will show you. It doesn't matter how many points you. Okay. Very good. So let me first let's come back to this again. Let's go back. Let's absorb the model a bit and change gears and do some basics of MATLAB. Okay. Are there any questions in the model so far?
Yeah, I had one.
Yeah.
That uh, like the model has in the model essentially we're doing comparative statics by changing fixed cost of
Yes. Yeah.
the and exit.
Yeah.
So I'm just wondering, like, why do we need this complicated machinery of the model? Like, why can't I'm thinking of like a very reduced form world where, like, you know, say we have some exogenous variation in
Hmm.
entry or exit costs, well, you know, say there is some like
Hmm. Yeah.
government regulation or whatever. So why can't we like just use that to
Okay. Yeah, yeah, of course. But let me ask you one question. Imagine I want to answer India liberalized in 1991. I see that as a decline in entry cost for firms because licenses are not required. I want to know how much it contributed to the GDP growth. How what regression would you run?
hmm, yeah, that would be hard because entry cost, like a lot of things are changing simultaneously.
Exactly. There are a lot of things that are changing simultaneously, but it's not even clear. You cannot, if you run like a GDP growth regression, you will have one, you will never you will never be able to answer that question because GDP growth will be a yearly variable. You will get 20 in 20 years. It will still, you will not, uh, and then you will not remember. You should only use model if it is absolutely necessary. Okay, so for instance, for general equilibrium effects, which is these macroeconomic effects, it's very hard to do it with reduced form analysis. So that's why you are willing to put the assumptions because you want to make a statement about the macroeconomic effects, which you cannot do it with the reduced form. So I'm very much in favor of doing reduced form work. And I do a lot of reduced form things to actually motivate the study. But in order to make the statement about how one reform will transform the economy or in good or bad way, it's very difficult to say it with the reduced form or any kind of quasi-natural or RCT kind of study. Okay. Are there any other questions? Okay. So we have seen a model. We are almost ready to put it into the computer. To put it into the computer, we need to know like a bit of like language of the computer. So there are many languages out there. You can use whichever you want, like Python or R, or R is not the best. You can use Python, Julia, or MATLAB for macro models. They are all very good. MATLAB is not the fastest. I am using MATLAB because this is what I learned when I was in PhD, but now it's getting out old-fashioned. But having said that, all these languages are very similar. Like in a sense, if you know the mechanics of one, you can learn very quickly the other one. All these loops, like for loops, while loops, and if and else conditions, the logic is very similar. So maybe the notation is a bit more different, but doesn't matter big. If you want to work with big macro machineries in the future, and you are asking me, oh, which language should I invest in? I would say invest in Julia, or Julia would be the best. Python is I'm not sure. I never worked with Python, but Python can also work. MATLAB is much easier than for me, at least, because I worked with it. So I'm sticking with it for until they stop producing the latest versions. Okay, so let me give you a very brief overview of this. Okay, what's happening? Should be slide. Okay. Do you see the slides? Okay. So there are 3 lectures, but I'm not gonna go through like all of the material, but let's see what can we get done. So This is how the interface of the MATLAB looks like. It's a 30-day like a trial version. You should download it and see how it works a bit. And of course, there are always like this open versions that are available to use. So this is how a window of a MATLAB looks like. Okay, so there is the circle that you see, not a circle, but kind of a oval, like the yellow colored, is the address of the folder that is active. For instance, I am using the folder GE model May 2020, which is a folder in intangible capital. There is a, you can select whichever folder you want to work with. Select the
Your
folder in.
Sampreet,
Hello.
is cutting a little.
Now it's better. Yeah. So you can select whichever
Also,
folder
sorry
you
to
want
cut
to
you.
work.
Also, if you can make sure the screen full screen, because it's
Ah, okay. That's new. Hmm, let me do one.
There's a better option to do it, like where this one is. Like if you go
Yeah.
here at the end where you zoom slides, right next to
So
it, the first option.
would be uh let me do one thing. And sorry, I'm a bit techno challenged. Okay, now it's better.
Yes.
Okay. So you see, like here, you have the you have this circle, the yellow oval, whatever shape is this. It's the address of the folder that is active right now. You can select the folder from this button here, which is like kind of a green arrow. There is a toolbox on the top, which is here, like you can import data, you can save work, whatever, doesn't matter. You can change the layout of this toolbox from this layout section here, whatever you want. You have, yeah, you have a files in the folder that are in the active folder. So in my 2.model GE May 2020 folder, these are all the files that are active. So these are all M files. So M is kind of, like the whatever you want, a syntax for the MATLAB files. Okay, so these are all M files that are active. Then all the data, all the variables that you will create in MATLAB will appear here. So this is the workspace. So there will be the name and the values. This is the command window. It's kind of an output. Think about Stata. You have a output and the do file where you write down the script. So this is where you write down the script. This is the do file kind of the analog for MATLAB, and this is the output screen. It's analog of the MATLAB. Okay, very good. Now within the this output screen for the MATLAB, which is here. Let me tell you one thing first, that you can always use this button to, if you have multiple screens or if you want to get out, take it out, you can always, how do you call it, undock. You can undock this screen and put it in a different screen. Sorry, this part of the MATLAB workspace and put it in a different screen, or whatever you want. You can undock any part. You see all these arrows are for undocking these different workspaces. Okay, so this command window here will tell you all the results similar to Stata. So here I'm doing different calculations. So 10 raised to power 9, 10 minus 2, and MATLAB will always answer you like in terms of answer. Answer is 8 if 10 minus. Okay. Um, symbol this 2 greater than arrows is kind of represents the command line. Here you need to give the command. If you are directly giving the command to MATLAB, you have to give it in this. This is the command line. Okay, then this is the folder from where you can select your current directory, because MATLAB will always want to work within the file, only with the files that are present in the current directory. So you make sure that you are in the current directory. Yeah. So this is the workspace I was talking to you about, all the variables. So these are the different variables that I have created. Some are arrays, some are column vectors, some are row vectors, some are structures. I will tell you what are structures. And these are the values. For instance, grit is a single, like it's kind of a single valued variable which takes this value, whereas this is the three-dimensional array, this is a two-dimensional array, and so on and so forth. Okay, so then the M file. So this is an M file. For instance, this is the name of my M file, main Davide ge.m. This is my M file. Uh, I'm using, so if I want to comment, I have to use double this percentage signs. Sorry. If I want to comment, I have to use this double percentage signs. And I'm using for housekeeping, which means I'm closing all the files that are active right now. I'm clearing the memory of the MATLAB. I'm pinning down the random number generation stream. Okay, so if you're using random numbers at any point in your code, in order to make sure you use the same random numbers, you have to make sure you are using same random number generating stream. Here I'm using RNG 100, but of course you can use whatever you like. Okay, if you want to run any code, you have to run it with from editor. It's called run. Okay, so you can run it, but you can debug the code. Debugging is very similar to all other kind of softwares. For instance, Python. If you are in Python, you can put a debugger at any line. So for instance, let me see if I have here. Yes. So if I put a debugger which is at line 10, then it will you see it as a red dot. Okay. Now if you run, if you put this run button here, then the code will run until this point. Okay. And it means that before that, everything ran correctly. So now you can go one line by line, which is step. If you do step, the code will, one extra line of code will be run. If it has error, then it will break. Debugger will break. If it is correct, then you will continue doing it until you break the code. Okay, so this is kind of a debugging. You can find the mistakes or the bugs in the code using line by line debugging. If you feel like there are, instead of doing step by step, you want to do the for next 20 lines, then you can put another debugger 20 lines below, let's say at line 30, and then you do continue. Then the code will run and then stop at line 30. Okay, so this is for multiple lines at once. This is for one line, one by one line. Okay. So how to define matrices in MATLAB? So I'm defining, it's very easy. You don't have to put generate or anything, gen g like data. You just say A is a matrix, which is a 3 by 3 matrix. Semicolon will tell the MATLAB that, oh, this is the first row, this is the second row, and this is the third row. A space will tell MATLAB that this is first column and second column. Okay, then after semicolon, again MATLAB will understand this is the first column, second column. Then again after the semicolon, MATLAB will understand this is the first and this is the second. Okay. The addition subtraction works very well. A plus B is addition. A minus B is subtraction. You can compute A, you can compute dot products, you can compute cross products. Dot products, which is the element by element multiplication, you have to put dot. Always dot. If you don't put dot, MATLAB is going to do a cross product. MATLAB is really good, very fast at doing matrices. Okay, so if you can convert all your codes into matrix format, MATLAB is the fastest. Julia and Python are the fastest with loops. You can do loops, but not with matrices. They are very slow with. These are the different commands you can use in MATLAB. These are another different like mathematical symbols that you have to. These are the things that differ across language. That's the annoying part. So if you want to say something is equals to the another, you have to put double equal to. If it is not equal to, then you have to put this. These are the symbols you have to learn. This I will skip. I will skip. Skip. I will also skip. Okay, let's go to the plotting. So plotting, the the graphs are much more beautiful in MATLAB. They are much better than Stata, but they are worse than R. R has much better graphing ability than MATLAB. Okay? So if I'm plotting like some two column vector, so two column vectors, so X is a column vector, Y is a column vector. I can say plot XY. So it will plot something like this. If I give the colors, so if I tell it the color should be this, so I'm giving the color code to the MATLAB. I'm giving the line style, which is dashed, and I'm giving the line width, which is 2. Then MATLAB will act, not instead of generating this, will generate like a very nice dashed line with the thickness too. Okay, so all this. These are 3D generate 3D plots instead of 2D. If you want to do 3D, you can do it. Okay, so this is an example. I will skip it. It's not the one we want to use. What we want to use is if else conditions. Please ask me questions if you have at any point in time. If I'm going too fast. Let me see. Okay. Okay, so if else statement. What is if else statement? It's similar to like if you have done any coding, if C, it's exactly the same. So if there is a condition, then statement, then if else if, then the condition, statement, else if, condition, statement, and until the end. For instance, this. Okay, I wanna I wanna I wanna update something if excess LD is greater than, else I want to update something else and end. Okay? You can nest more things. So I will, if this is happening, then n should be 1. If this is happening, then n should be 2. And if this is happening, this. So you can have multi like layered if else statement, nested if else. For loop is the same. You can have like nested for. So I'm saying for I goes from 1 to 5. So I can take 5 values. It can be 1, 2, 3, 4, 5. Within that, for j 1, 2, 3, 4, 5. So for each I, so first MATLAB will say I equal to 1. Then it goes to this line, say j equal to 1. Then it will compute aij. Then it will compute for j equal to 2, j equal to 3, j equal to 4, j equal to 5. Then the bigger loop. Then I will become 2. And then again j 1 to 5. Then the bigger loop 3, I equal to 3. Then the smaller loop. So always it will do smaller loop than the big loop, smaller loop than the big loop. Okay. There is a final thing that we use a lot is the while loop. While loop is that keep looping. So here I have I for loop will loop until you reach the end point, which is 5. Okay. While loop is kind of a mixture of for and if else statement. So I'm saying while this is true, keep on looping. Okay, so while 2 raised to power a is less than n is a n, always keep on updating a. Okay, so it's kind of a combination of four and uh, four and if else loop. And you can see that this is very useful because we will use it a lot in macro models. For instance, particularly when we want to pin down the prices in the economy, we will use this thing. Okay. So here, for instance, there is an example of bisection method. So I am a big fan of bisection method. I learned it in my engineering school. I think everyone of it's quite it's quite possible that many of you are also engineers. If you are not, then bisection is something that you should know. Bisection is very simple to understand. Let me first tell you what is bisection by a simple graph. So do you see the paint? Okay. Do you see the paint, right?
Yeah.
So
Yes,
Mhm.
yes.
okay, new. Don't see. So bisection is I'm gonna okay. So uh, bisection is that imagine this is my zero line. This is my zero x-axis. No, actually, this is x-axis. Okay, and this is my function y. This is my function y, which is the function of argument x. Okay, this is x. This is y of x. Let's say this is my whatever x. This is 0, 0, 0, 0. I want to compute the value of x star where y of x is equals to 0. This is what I want to compute. Okay? The 0. I want to compute x star. This is x star where this line crosses x equals to 0. Okay. Bisection tells you very simple. Say, okay, you need to give me a bound. Bisection say, give me a bound. I say, okay, I wanna, I don't know the bound, so I wanna choose a big bound. So let's say I choose a big bound. This is a lower bound of x. This is the upper bound of x. Okay. So I use a big enough bound such that my zero lies in between. Okay. So this was my upper bound, sorry, lower bound. This was my upper bound. Then I will say choose any starting point. This is my x0, which is my starting point. Okay. Compute y at the starting point. Okay. If it is greater than 0, then lower bound should be updated and it should be x0. Okay. So now you see that yx0 is greater than 0, then lower bound will become this. Okay. Then I say, okay, what is my next? I will say, okay, next will be some sort of middle point between new lower bound and the old upper bound. So let's say this is the middle. This is my x1. Okay, then I compute y of x1. This is less than 0. Then I will say, if this is less than 0, then this is my new upper bound. Okay. I'm gonna do it until I converges to my x. This is bisection. Does this make sense? Yeah, very good. Any questions? Okay. So this is what I'm doing here. Somebody told me that multiple, whatever. Okay, so here is the bisection method with the while loop. Okay, so I'm saying if the critical is the difference between, I will tell you like the two conditions that I have. Let's say I will tell you what are these conditions. I'm saying there should be a maximum of iteration. If the maximum iteration are greater than 1000, just break the loop. Like I don't want to run it anymore. I'm computing excess labor demand. So excess labor demand is the labor demand minus labor supply. So if it is positive, then it's excess. So I want to make sure there is a price that equalizes labor demand and labor supply. So I write down a model where I come, which gives me the output, which is the excess labor demand. I'm saying if the excess labor demand is greater than 0, then update the lower bound with the guess, right? So the demand is very high. It means you need to update the lower bound. If it is the opposite, then update the upper bound. It means demand is very low. Okay? So I will do it. That my new page will be, I'm using a guess, which is I'm using updating rule, which is quite random. I'm saying it should be a mean of upper bound and a lower bound. Okay. And I'm computing the critical value, which is the difference between the new and the old guess. Okay. And this is what I have here. So if the difference between the old and the previous guess is very small, it means you have converged. You are very close to your zero. That's it. And that's why you will, and here I'm updating my guess. So I will do it. And when the code will converge, I will have my wage that clears the labor market, which is that excess labor demand will be. Is this okay? Good. Okay. So this is what we are gonna use. Uh, I'm gonna stop here now. There are many other things in this in this uh, in this file that are fun and you should go through it, but I will not cover it because I want to go back to the model. But what I will do now is take a 10 minutes break and we meet around 14:45. Sorry, in 10 to 11 minutes. Is that okay, Arushi? Okay, perfect. Please, meantime, go through these slides very quickly, and I'm happy to answer a few questions. I'm going to use this bisection method that I just showed you to pin down the prices in the Oppenheim model. So it's kind of an important thing. Okay. See you in 10 minutes.
Yeah, hi. So I think in the model, I wanted to ask two things. One, the assumption that you have, which we discussed yesterday, was the decreasing returns to scale.
Mhm.
That assumption is there because you wanted your value function to be convex, right? In the equilibrium
Say it
on
again.
productivity. So when you show on the model, in the model you have value function on productivity, and productivity itself is coming from a probability distribution function.
Yeah.
The decreasing returns to scale is ensuring that your value function is going to be convex, which is
Yeah.
exactly what you want,
Yeah.
right? So I was just thinking that I was just thinking in that way. So the assumption is giving you the convexity of the value function.
Yes, exactly. That's true.
Right.
Um, the convexity is coming from decreasing returns to scale. Exactly. Yeah, that's true. But we do not need convexity of the value function. We need
Why not?
in productivity. We need an increasing value function. It can be in productivity. It can be convex, linear, or concave. But in this case, we have convexity, which serves our purpose. We need an increasing value in productivity. We don't need convexity.
Increasing value in the sense that
It can be convex, it can
yeah,
be linear, it can be concave.
but it's decreasing, right? If you have a convex,
I can have convexity increasing like this, I can have linearity or I can have concavity, but it can always, it should be increasing. But it
Increasing
can,
point, I get it, because you want that threshold where you
yeah,
can check that
yeah,
exposed forms will exist,
yeah, yes,
right? Because the cost that you're introducing.
yes,
Right.
exactly.
I was thinking more in terms, if I want to analyze the same firm dynamic setup,
Mm,
let's say for the service sector, where
yeah.
the function should be increasing returns to scale, that would make more
You
sense.
cannot have increasing returns to scale in this production function. So we can talk about it. Let's have a separate chat on this. It's important issue. You have raised very important question. In
Right.
this model, you cannot have, because if you have increasing returns to scale, firm size is not like bounded. Firm will be unbounded because it's perfect competition. So if firm can produce at a decreasing rate for a given price, firm wanna
Mhm.
produce infinite, right? So here firm has a bounded size just because marginal cost is increasing because of the decreasing returns to scale. Even with constant returns to scale or with increasing returns to scale, firm wants to become infinitely big. So then you need a force of market competition that, oh, if firm wants to become infinitely big, then firm has to lower price. So firm is not a price taker in anymore. So you need some sort of imperfect competition. Competition, like a serious notion of competition is required. So you need to go into like monopolistic competition, oligopolistic, whatever you want, you can have it. But in this model or any model of perfect competition, you cannot have. You can with firms, with a lot of firms, with heterogeneous
That I
firms.
agree. I mean,
Yeah,
you're right. Yeah, I
yeah,
completely agree. Yeah, let's talk about this later.
yeah. Like we can talk about the Mallets model is a good example where you can have increasing returns to
Yeah,
scale.
exactly. I was coming to that model as well. That
Yes,
model had in my mind.
yeah. It's the same model. It's the same
Mhm.
model, but instead of perfect competition, they have a they have a monopolistic
Monopolistic
competition.
competition, right?
Yes.
The
So you
it
can
does
have
increase.
whatever scales, returns of scale you want. Like
Yeah.
not whatever, but you have more degrees of returns to you can go above one, not crazy above one, but you can go you can have this alpha. Let me share my screen. um, okay, you can have this alpha, which is the returns to scale, to be greater than one. Here it is always less than one, which means firms are increasing, the marginal cost is, but we can talk about it. If you write me an email, we can schedule um, a chat.
All right. Thank
Yeah.
you.
Yeah. So okay, so let's go to the main. It took us 3 days, but we are finally here. I hope you guys have like, took something from the model and you still remember it. We are now gonna put it into the MATLAB. So there is this file called M2 main2. This is OpenAI model. And and again, I am doing some housekeeping, like I'm closing all the files. So again, look, I'm gonna put a debugger. So this is a debugger. So if I now run, uh, it will run at this point. So what it does is that it cleaned my workspace over this. Do you guys see my screen, right? Okay. So you see that the workspace is cleaned, and these are the commands for how. So you can, you should always have these three things in the beginning of the file so that nothing can go wrong. Then I'm establishing my random number generating stream so that, like I get the same random numbers every time I run this. Okay, now I can go step by step. So first I define my alpha. Alpha is my returns to scale. So you see like alpha is 0.64. So I'm solving this model first for some parameters. And then next I will tell you, if you want to calibrate some parameters using some simulated method of moments, how do you do it? Like how to estimate the model itself. So let's first solve the model. So there was this interest rate. Actually there was no interest rate. There was a discount factor. I'm going to assume my discount factor is 0.80. So this is my discount factor. So remember, if you look at the slides, my discount factor is 0.80. This is what I'm assuming. Wage is going to be 1. Remember, either I can solve for price or I can solve for wage. So because we care about real wage, the economy can always be solved for a relative price, but not an absolute price. So I'm going to pin down wage to be 1. The fixed cost of production is 10. The cost of entry is 40. Theta is 0.9. So let me tell you what is theta. Theta was it's rho. Actually, it's not theta, but I defined it as theta. Doesn't matter. Okay, so now I'm discretizing my productivity space. So I'm defining here 501, let's say. So I'm discretizing my productivity space into 501 points. You can do it for 50 points, 10 points. I will show you it doesn't matter. Okay? So I will put a debugger here. I will do continue. And now my code has run until this point. So this is, I will use this token. Token will do. So there is a code token I have given you as well. You can study it, but I'm using this function directly, and this will discretize the distribution for me. So I'm telling token that this is my Markov process. Okay, so this is my Markov process. So token is asking me what is rho, what is z bar, and what is this sigma. If I tell token what are these parameters, token is gonna discretize the distribution at number of points you really want. Okay, so I'm saying token discretize the distribution as 501 points for z bar, that is 0, for persistence rho, which is 0.9, and the standard deviation 0.2. I'm cutting the distribution at the 5 standard deviation from left and right. Doesn't matter, you can keep it. It's just to remove the outliers. Okay, so this is not the most important one. These are the important ones. This is persistence, this is standard deviation, and this is the dimensions that you the number of points you wanna. Okay, so if I do it, token will give me the productivity. Okay, so this is the productivity, different levels of productivity. You see, like this is, I was trying to tell you, I do it for the odd number of points because I will always get 0 in the middle. That's why I do it. But it doesn't matter. I can do it actually for 5 points. Let's do it for 5 points. If I do it for 5 points, then let me put it here, debugger. If I do it for 5 points, then these are my productivity levels. There are a few form, this. The probability, the transition probabilities are this. Okay, so this is a probability of Z1 to be Z1 next period. This is a probability of Z1 to be Z2 next period. This is a probability of Z2 to Z1 to be Z3, Z1 to be Z4, Z1 to be Z5. And similarly, this is a Z2 who will be Z1. This is a Z2 who will be Z2 next period again. Z3, Z4, Z5, and similarly for each. You can see that the diagonal elements are are basically have a highest probability. This is basically why, because we give a lot of persistence. Okay, so if rho is very high, then productivity will be very persistent. So the probability that I'm today Z1, if I'm today Z1, tomorrow I will again be 0, Z1 will be very high. Okay, so remember, if I put here 5, let's say I put here 5. Instead of 0.9, I put 0.5. Then you can see now that the persistence has decreased a lot. Okay, so the diagonal elements are much smaller. The transition probabilities of being in the same state tomorrow as today is much lower because persistence is much lower. So either you can do persistence or you can increase the standard deviation of the productivity process. This will also give you similar. You see, like you have decreased and you have increased this the deviation of them. Okay? So you can play with these things. It helps you to understand more. Okay, so I'm going to define, remember, I'm going to do a while loop on prices. So there is this one price P naught that I want to pin down such that the free entry condition holds. I will use a bisection method, which means I need to define an upper bound and a lower bound. I need to be general enough. So I'm saying my upper bound, there is a guess. This is a guess, like you will never know. You have to run the model many times to understand where is the price, where the price lies. It will never run in the first time. There will be a lot of errors. So I am saying lower bound is something like this, the upper bound is something like this. Then I'm defining V prime, this continuation value. Remember, I don't have the continuation value, so I need to guess it, right? So this is the slide uh, here, right? So I do not have my continuation value. So I told you that I will use it by value function iterations, and which means that I need to guess it. Okay. So I'm saying I will guess the value function in the first period as 0, and I need to guess it for the each Z1 type. So it should be of dimension 5 and 1, right? So dimension is 5 for each Z. And I'm saying maximum iterations will be this, like I'm putting a random number. You can put like smaller, bigger, but doesn't matter. Okay. Then I have a for loop for I equal to 1 to max iter. Okay. I'm going to do a for loop, and I will stop it at the maximum iteration, because if it doesn't converge until this, it means it will never converge. So something is wrong. So that's where I'm stopped. My first guess will be a mean of high and low price. This is my first guess. Now, given this price, I can compute the optimal labor or the firm size because of the first order condition, right? So if you want to know what is the optimal labor, then you need to go here. So if this is my production function, given the price, my labor is this. This is the labor. Okay, slide 38. This is from where I'm taking. So this is I'm putting here. So this gives me the N star. I can now compute profits because I know the N star, I know alpha, I know price. This is my revenue, this is my wage bill, and this is the fixed cost of production. Okay, good. Okay. So if this is my fixed, these are my profits, then I can now compute the value of the firm. So for the value of the firm, I am doing another loop. Remember, I do not know, so I have to use this value function iteration. So I'm going back to equation this, okay, this one. So I know my profits, current period profits. I know a guess for VJ, right? I know a guess for VJ. And because I know the guess for this, I know my profits, I can compute the value today. Okay, this is what I'm doing. I'm saying I know my profits, I know my V prime, which is a guess. So let me now run until this point. Okay. Yeah. So I know my V prime, which is 0, 0, 0. This is my discount factor, beta 0.8. This is my profits, which is, you can see they are something like that. And I can get my V, right? So the V is this V. So the value of the firm. Okay. So the value of the firm I have. Then what do I do? Then I say, what is this value of the firm? I said, oh, value of the firm is actually this. My guess was 0, 0, 0, but the value of the firm is not actually 0, 0, 0, is something else. Then I took a norm, means the distance between the value. Okay. So he said, if this difference is very small, it means my guess is actually the true value. So then we are good. We have the value of the firm. Otherwise, break. Oh, sorry. Then break the loop. Get out of the loop. We have the value of the firm. We are good. End. Okay. Then V prime is equals to V. Okay. So I have to do this loop until until this difference is less than this point 10 raised to the power minus 1 raised to the power minus 10. Okay, that's how I get this value of the firm. Is this good? Okay. Now let's go now until this point. So once I have the value of the firm, which is now I have the value of the firm, something looks like this. I have the value of the firm. Now I can compute what is the the value of entry. So the value of entry is very easy. I know my value of the firm, which is here. I need to compute an expected value of entry, which is the exogenous distribution of what I will be. So there is a distribution mass of 0.009 that I will be Z1 type, 0.13 that I will be Z2 type, 0.72 that I will be Z3 type, and similarly Z4 and Z5. Okay, so I'm computing the expected value of this. Because I will not produce the same period, the first period I will enter and then I will produce the next period. This is an assumption. You can always make them to produce the same period as well, doesn't matter. So I'm discounting the profit by one period. So my discount factor, that is beta. But I can also remove them, it doesn't matter. I'm just making this assumption that they will produce the next period, not the same period. Okay, so if this price was the price of equilibrium, then the expected value of entry should equals to the cost of entry. So this should be 0. Okay, let's see. This is not 0. Actually, this is very high. It means that the value is too high. Prices are too high. So we should reduce the prices. Okay, this is what I'm going to do here, bisection. What I'm saying is if value is too low, if value this thing is negative, it means cost is too high. Then the lower bound should adjust. If cost is too low and the value is too high, then the upper bound should go down. Okay, such that you converge to the midpoint. Always remember this. Okay, so if you are positive, then your lower bound adjust. If you are negative, your upper bound adjust. Okay, this is what I'm doing here. I'm gonna do it until you reach the 0, until VE is exactly 0. If this is 0, then I have my equilibrium price. Okay, this is what we are gonna do. And just for accuracy, I'm gonna increase my points on Z. And okay, so I have solved the model. So the equilibrium price turns out to be here. So the equilibrium price is 5. The value of the firm is something like, the value of the firm is something like this. Okay, so I will show you the plot of this. So if I now plot the value of, let me show you actually the plot of this. Plot. Yeah. So you see, this is the value of the firm. Not exactly. No. Yeah, so this is the value of the firm. Okay, so this is on the x-axis I have the productivity, on the y-axis I have the value of the firm. You can see that it is increasing convexly. This is the graph that I was showing you in the slides. Okay, so now we have solved for the prices. So what is left? Remember, I have first step I have solved the smaller loop is to solve the value of the firm. The bigger loop is to solve the prices with the free entry condition. Then I need to solve for the distribution. The distribution is you can solve easily because you can just take the inverse for a scaling factor m. So let's do that. So first I will compute my static exit decision, which is that if my profits, like with the probability times the V prime is greater than 0, if the expected value is greater than 0, then I will stay. Okay, so this will take this staying decision. So this will tell you who will stay, who will not stay. All the zeros are not staying or the ones are staying. Okay, so you can see that the more productive firms are staying, or less productive firms are exiting. Now I need to compute my omega. So what is omega? Let me show you. Omega is this. The decision to stay times the transition probabilities. So this is what I'm doing here. I'm multiplying the transition probabilities with the decision to stay. So this gives me my omega. Okay. So if I have my omega, this is my distribution of entrants G. Okay. So this is my distribution of entrants Z, which is here, actually this one Z here. Okay. Then once I know G and omega, then I can get my lambda, which is the stationary distribution. So this is the stationary distribution. Stationary distribution for m equal to 1. This is the this is the distribution. Of and transition matrix. Okay, very good. So once I know my, so this is, let me tell you, so this is my stationary distribution of firms. Let's see how it looks like. Let me plot it. Plot the, this is the stationary distribution of firms. This is how it looks like. Okay, so there is kind of, looks kind of normal. Okay, but there is a bit of selection at the left tail. Now, how to compute M? Remember what is M? M is, now again go back to the slides. We know that M is nothing but total demand divided by total output at M equals to 1. Okay, so we have computed mu for, so this we have computed for mu1 and P star. So this is for mu1 and P star, and then we will compute this for M star P star. Okay, this is the goods market clearing. Yes, Niranjan.
So discount factor that you took, that was exogenous, right? 0.25.
Yeah, 0.8.
0.8 or
It's yeah, it's 0.8. So the discount factor is the 1/1 plus interest rate, right? So
yeah. So if I'm thinking correctly, the discount
yeah,
factor should be more, I mean, higher than that. Although, I mean, you want to establish with the relationship with the interest rate,
yeah,
but at the same time, what I had in my mind, that the distribution that is shown, right, it was a little left skewed. So
yes,
firms are choosing to produce in the next period and exiting more,
yeah.
right?
The firms. So let me come back to that point. Okay, let me
Yeah,
come
I
back.
was thinking it could be just the selection effect.
Let me show you the distribution in 1 minute, and then you tell me. I will tell you the selection is happening. Okay, that was, let me compare the distribution for you. Let me just finish these things. So once you have the, so this is my demand. Remember that here I'm choosing demand to be, it doesn't matter. I'm choosing demand like as a function of price. So if prices are high, demand is low. But you can always also have here 100, it doesn't matter. Okay, this is the total supply at M equals to 1, and therefore you have your M. And then I readjust my distribution of firms with M. Okay, so this is my new distribution of firms. If I want to compute my entry rate, I just need to divide M by number of firms. Okay, which number of firms will be the total sum of lambda. Okay, so let me show you. So in this economy, total number of firms were so the total mass of firm is 0.0028. The entry rate is around 25%, and the exit rate should also be the same, around 25%. Okay. You can reduce, let me tell you now one thing, how let me reduce this to 6. No, let's keep this. So I will now tell you how to calibrate this entry and exit rate in few seconds, but let me first plot to answer Niranjan's question. Okay, so here is the distribution of firms. Okay, so this red one is the ergodic distribution of the firms. Like, remember, we assume a log normal distribution of productivities. So kind of a left skewed but thick tail. Because there was selection, the less productive firms are exiting the market. So the distribution of firms is shifted towards the right. That's the blue line here. Okay, that's the blue line. That the distribution of the firm is shifted towards the right because there is selection. The distribution of the employment is even more shifted towards the right because of the convexity. Okay, which means that firms that are very productive, they are much bigger than firms that are less productive. So the left tail of the employment distribution is going to be very thick. And this is an important, and this is pinned down by this returns to scale parameter. And this is important. This can explain why the distribution of firms is very thin tail in India relative to United States. And then the question can be like, why the returns to scale are lower in India relative to United States? All these questions, all these things hinges upon this, like very few parameters that we have chosen. And these are the parameters that we need to calibrate for, whatever moments you have in the data you want to match. Okay. So imagine you want to compute the returns to scale by matching the share of employment share in India. Let's say this is what you want to compute. You want to say, okay, I see that employment share distribution in India looks something like this, the yellow line. What does it imply for the returns to scale of the production technology? This is what I want to understand. So you have to run this code multiple times. So you have to run this code for different returns to scale. Okay, this is what I'm doing in this in this file main3. So what I'm doing is that there are now 3 loops instead of 2 loops. So I am first saying, let's have alpha that is at 0.63, 64, 65. You can have much bigger grade, doesn't matter. But this is for the exposition purposes. I'm solving the model for the 3 alphas. Okay. I'm saying solve this model for 3 different types of alphas and then store the distribution of the employment moments here. Okay. So here I'm storing the distribution of the employment moments. Okay, this is not what I want. Okay, so this is the distribution of, so this is the sum of employment of all firms below 20 employees. This is the sum of employment of all firms below 50 employees. This is sum of employment of all firms below 100 employees. This is sum of employment of all firms below 500 employees. And this is the rest. Okay. And you can see that I can compute it. I computed this moment for different levels of alpha. So all these moments have 3 values because there were 3 values of alpha. Now, in the model, these moments will be different depending upon alpha. But in the data, imagine you compute this thing in the data and turns out to be 0.01, 0.04, 0.08, 0.5, 0.3. This is, I'm just putting random numbers, but this you have to compute in the ASI or Provis, whatever data you are using. And now I'm computing the distance between the moment that is implied by the model and the moment that is in the data. So here, the moment is the share of employment for firms less than 20. And I'm saying, oh, this is 0.003 for alpha this, it's 0.004 for alpha 3, and in the data it is 0.01. Okay, and I am doing it for all the moments. So I'm here matching 5 different moments of the employment share distribution, which will try to capture the distribution itself. You can increase this number of moments or decrease, doesn't matter, depending upon the fit that you have in mind. Okay, and then I will say sum the distance. I will say you have 5 moments, so it's an over identification for 1 parameter. So I'm going to sum the distance. That's kind of a over identification where where I'm just squaring the moments and adding up all the distance. And then one way people use is that always choose the parameter that gives you the minimum distance between the model implied moments and the data moments. So here you can see that the distance is increasing. So if I just have three different alphas, then I will choose the alpha which is the lowest because it brings me closest to the data. Okay. I think I spoke too much because I got overexcited. I wanted to share all these things with you, but now just throw the questions at me. I think it's a lot to take, but please.
Yeah, say something like a couple of things.
Hmm.
So instead of token, if you use like Host in the Markov chain process, I don't know
It's
if
the
MATLAB
same.
has it. I don't know if MATLAB has it. So,
I can send you. I have the code for Host if
oh,
you're
acha,
using the yes.
and what did you find? Like,
It's the same. It's the Host is very good if you have very thick tail distributions
yeah,
because it takes care of the tails very well. So it's
right.
better in that sense. Token is not very good at the tails. So if you have very extreme value distribution, don't use token.
Yeah, so when I saw that, that's what I thought. I mean, why not
No.
use?
You
And the
have
second thing,
token, you have House. There is one more, but I don't remember. Tell me.
you can also just check the correlation from the model array and the data, sorry, model array, the values that you have got for each
Yeah.
moment and the data itself. Would that be sufficient? No, if you just check the correlation between the two matrices, rather than taking the distance, then
What
that
would be the correlation?
if the correlation is very, very high, correlation in the
No,
sense that
yeah, correlation can be high, but you can still be very off in terms of what's the returns to scale are. So here I'm estimating one parameter. Imagine you are estimating 3 parameters and you have 20 different moments. Then first you need to make sure that the parameters and the moments have a positive like or negative or positive correlation. But you need to choose the values of these 3 parameters such that the moments that the data gives and the model gives are relatively close. Yeah, they will never be the same because it's over identified, but you want to minimize the distance. That's the simulated method of moments, what they call. We are still not having any standard errors because this is a simple model. You can solve it multiple times. But if you want to publish a paper, you really need you will have like a much complex model that will take like 15 minutes to solve once. And if you have to solve for 3 parameters for different combinations, it will take forever. So, um, it's okay if you don't report standard errors in calibration or simulated method of movement, at least in macro. Um, so correlation is not enough. You need to have you can specify any criterion, but there should be a criterion to choose parameters.
yeah, the distance criteria, I mean, the algorithm that I have used also, I use distance criteria, but I also check the correlation itself. That's what I've done.
No,
And then
correlation is important because correlation tells us is this moment informative about this parameter. So that's kind of a
yes,
sensitivity analysis that you need to do before you do the calibration. Okay, so you need to make sure that like here I knew that alpha is very informative about employment share, but many times you don't know, so you need to do that sensitivity analysis. That's true.
yeah.
Correct. Good. Thanks for the comment. Are there any other comments or questions or anything? Okay, so I think it was a lot of stuff, but I'm happy to answer questions if you. I'm happy to do office hours also at next week, not this week, but next week. If you go through the material and you tend to have some questions, and if there is enough demand, I'm happy to do office hours as well. But I hope it turns out to be useful for you guys, and I see your papers in working papers at least using these methods. That's it from my side.
Thank you so much, Sampreet. This was an absolute pleasure. I think, like you said, it was a lot to take in. So I think it would be like, I really appreciate that you could like take office hours next week. So what we can do is maybe like try to go over the materials at a slower pace ourselves this week. And what we can do is maybe like send you an email about scheduling office hours, because I think the reason that, yeah, I mean, for me also, I've kind of seen the entry exit models in the context of my IO class that I took second year. But yeah, it is definitely a lot. But thank you so much. I think this was like a really great starting point for most of us. And I think it will really help build on some of the more reduced form work a lot of people I know are doing here. Yeah, thank you so much.
Thank you for the having me. It was really nice to talk to you guys, and I hope it will be useful. Okay, see you.
You stay in touch.
Bye. Have a nice evening.
Okay, thank you so much. Yeah.
Thank you
Thank
so
you.
much.
Bye.
It has been
Bye.
helpful.
Thank you so much.
Thank you.
Hello.
I just wanted to ask Harshadi, for the office hours. So will you be writing email